This is part of a series, the main topic that I've been working on for the last couple of years, which is to extend beyond this Heckenberger-Kolb situation, beyond these irreducible quantum Flag manifolds, a very special type of quantum Flag manifold, to a larger class, basically to try to produce non-commutative geometries for all of the Flag manifolds, in the ultimate hope that we can then go up and actually do it for the quantum group itself. The biggest open problem, I guess, in the non-commutative geometry of quantum groups. So what I have been speaking about for the last number of years is taking the A-series full Flag manifolds, and by restriction, all of the A-series Flag manifolds, and finding a Q deformation of the anti-holomorphic part of the Dalbo complex. If that doesn't make much sense to you, don't worry, you'll see it in a bit more detail here for this specific example. But what we haven't considered is the entire Dalbo double complex. It's just, so this talk is about restricting to the simplest example outside the Heckenberger-Kolb setting, which is going to be the full Flag manifold of quantum SU2, build upon what we had before with my work at Peter Sundberg in Karlin, and just explore what it looks like for this example. Hope as well is that this example is actually extremely nice, and it's got more complications. And in some sense, it's more difficult than what is happening with the irreducible flags in Heckenberger-Kolb. There are new phenomena that happen, new phenomena that arise. But in another sense, it's actually closer to Podlesh, the most well understood, well studied example of non-commutative geometry in quantum groups. Basically, this is, we hope that people will be interested in this example, given that it's so attractive and that it's so nice to work, and that they're, it will generate sort of a new Podlesh. Let me. Okay. So let's just recall some standard material. Again, you've all heard about it many times. Let G be a complex semi-simple Lie algebra. So it falls into the classification of complex semi-simple Lie algebras into four families, A, B, C, D, and the exceptionals. Then G is going to be the corresponding simply connected compact Lie group. Then for any Q, we're going to restrict. These things make sense for Q in all of the complex plane, but then of course you're going to get into the situation of roots of unity. The real structure becomes more complicated, etc. So we're going to just restrict to positive R, which is a standard thing to do. Then we have a dual pairing. Again, the dual pairing doesn't depend on Q is equal to R. Q is equal to R is a convention for this talk. And we have a dual pairing of composite triangular Hopf algebras. Now, when Q goes to 1, we're going to recover the algebra of representable or polynomial functions, and O of G, and we recover the universal enveloping algebra. That's not entirely true. In fact, you're going to get an L-fold cover of the universal enveloping algebra. This is sort of a technical detail, where L is the rank of the Lie algebra that you're looking at. Okay, so just the general setup. But for this talk, we're actually going to be concentrating on low rank examples, because this is what, there was some calculation for this to work. That's where Junaid came in, because we wanted to test how these things behaved in a nice low dimensional example. So what I'm going to do, I'm trying to say that this is sort of like a next step in Podlesh, the higher rank Podlesh almost. So in order to give you some idea of what that means, let's just recall what Podlesh itself looked like. So we take the most famous example of Drinfeld-Jimbo coordinate algebras, the Drinfeld-Jimbo quantized enveloping algebras. So quantum SU2 and UQSL2, the C-star completion of the one on the left of OQSU2, of course, being the most famous example of a compact quantum group, the first one that was discovered by Voronovich. Now we're going to call the invariant subspace. So UQ of H is going to be the Q analog of the Cartan. Okay, these are like, if you think of SL2, it's going to be trace-free matrices. You've got your entry in the top, the 0, 0, 1. You've got your entry in the bottom, 0, 0, 1, and it's the 1 minus 1 on the diagonal. That's the Cartan subalgebra of your Lie algebra. And then that has an analog, direct analog for UQSL2. It's the thing generated by the Ks, if you know the relations, the generators of UQ and G. What does it turn out to be? In fact, it's just the Laurent polynomials. So it's a copy of the Laurent polynomials that live inside an UQSL2. And there is a natural action. So if you take this dual pairing that you have here, you can use that together with the coproducts to turn the pairing into an action of U cube SL2 on O cube SU2. And in fact, this works at the general level of O cube G and U cube G. And then what we're going to look at is the invariant elements inside there, the ones upon which this Laurent polynomial act as the identity. Okay, so that the generators of the Laurent polynomials act as one, act as the identity. And that's going to give us a subalgebra, and that subalgebra is a sub-co-ideal inside in O cube SU2. And what happens when Q goes to 1, it actually reduces down to the algebra of functions on the algebra of polynomial functions on the 2 sphere. Okay, and this is the Podlish. You can also, if you think about it in terms of Z gradings, this action here of your Laurent polynomials will give you a decomposition, a Z algebra grading, and this will be the degree 0 part of it, okay, which is what happens in the classical setting. So this is what I was just saying, is that the action of the Laurent polynomials, because it's Z algebra grading, is O cube SU2, it decomposes into the direct sum, Z algebra grading. The degree 0 part is, of course, the Podlish sphere. This is the decomposition of left O cube SU2 modules, or equivalently U cube SL2 modules. So it respects the symmetry that O cube, the U cube SL2 symmetry of O cube SU2. And for each K, the subspace is clearly an O cube SU2 bimodule because it's a Z grading. So multiplying 0K by E sub K by E sub 0 is going to give you something inside an E sub K 0 plus K, i.e. E sub K. So it's a bimodule. And in the Q is equal to 1 case, this bimodule, which is invertible and hence projective, it's a finitely generated projective module over this. So it actually reduces down to the sections of line bundles over SU2 by Swan-Serre. Okay. No, classically, the de Rham complex of S2, so it's a differentiable manifold, so you can consider the one forms, you can consider the extension of this to the de Rham complex. And you can ask then, if we're able to deform the line bundles, can we deform the de Rham complex of this thing? And in fact, we can. There's a direct non-commutative quantum generalization of the de Rham complex. It's if you want everything to still respect the symmetry, you want this to happen inside in the category of UQSL2 modules, then this makes it essentially unique. Okay. I could give you the criteria for the uniqueness that actually completely defines it, but if you just take away this idea that once you put the symmetry on it and you want to have the correct length of the de Rham complex, then everything is unique. There's only one of them. This is a really great example of a non-commutative geometry. So it's something that has been built upon by many people in many directions. So, you know, if you want to go into conspectral triples, it's all based on this. If you want to go into compact quantum metric spaces, it's based on this thing. If you're going into more complex geometries, we'll see in a while, this comes from this example. So it's a major example in the theory of compact quantum group, of the non-commutative geometry of quantum groups. And it has the benefit that everything actually works. It's sort of a, so what we wanted to do is try to extend this up. But beforehand, let's just recall an observation of Majid from almost 20 years ago now, that in fact, these one forms, so if you go back, this is the de Rham complex. Here we are. It's a complex, but in a classical setting, if you have a complex manifold, then your one forms, at least a complex surface or a Riemann surface, then your one forms are going to break up into a direct sum, and they're called 1, 0 and 0, 1. And then the degree 0 and the degree 1 part, they stay the same, but it splits up, and then your differential, your exterior derivative splits up into a direct sum. So this is just the exterior derivative and projection onto the left, exterior derivative and projection onto the right, and then this is just restriction of the exterior derivative to here. And this thing is actually a double complex. Okay, it means that if I apply del squared, del bar twice, it goes to 0, that's obvious. Del I apply twice, it goes to 0, that's obvious. But if I go up this way and then that way, or I go this way and that way, they'll differ by a minus sign. And that's equivalent to the fact that d squared, their sum is equal to 0. So Shan observed that this decomposition, this classical decomposition coming from the complex geometry, extends to the non-commutative setting. Okay. And when I was speaking in the introduction about the anti-holomorphic part of the Dolbeault complex, it's this part here. And this is related to, if you know something about spin manifolds, if you tensor this by a line bundle, the line bundle E minus 2, this will in fact give you the spinor bundle, if that means anything. But what's very nice is that because this thing is two-dimensional and because of the representation theory, and you know that these things are equivariant vector bundles over the sphere and so on, classically, the 0, 1 part is a line bundle, the 1, 0 part is a line bundle. Of course, the bottom is the trivial line bundle, and the top, because it's orientable, it's classically an oriental manifold, is also the 0, 1. And this description carries over directly to the noncommutative setting. So this is it completely in terms of line bundles. You can understand this thing, these components is living inside a quantum SU2. A very nice picture. So, as I said, this thing has led on to any example, I guess, of a noncommutative geometry in quantum groups is built upon this. So the natural question is, how can you generalize it so that we can have build upon more things? Classically, S2 is CP1. So the complex projective line is the same thing as S2. So a natural thing to go from, how do you what do you generalize to after looking at CP1? You generalize to CP2. You might be tempted to look at this as S2 and want to go up to S3, but it turns out S3 is SU2, and that's the Hopf algebra, the quantum group itself. And that's extremely difficult because you haven't quotiented out some of the worst of the noncommutativity, I guess. So trying to generalize up to S3 and so on is actually quite difficult. So the easier way to generalize is to go from CP1 to CP2. And that's the work of Heckenberger-Kolb showed that this is indeed the case. And you have a direct Q deformation of the de Rham complex, this decomposition into a diamond, this Hodge diamond, that also carries over. We can express this in a very nice picture. So for CP2, we have this. You see that as the rank gets higher, your diamond goes like this. You can understand why it terminates, because this is an exterior algebra classically. This is an exterior algebra. In the quantum case, it's a Q exterior algebra. So eventually this will stop. And I guess you see that as the dimension of your complex manifold becomes larger, the number of summons in the row becomes larger, because it should form a diamond shape. Okay. Same thing happens here. You see now, if I apply this twice, then it's less trivial that this goes to 0, but it does go to 0. And if I go around any one of these diamonds that make up the larger diamond, then we're going to differ by a minus sign. It doesn't commute, it commutes up to a minus sign. And so this is a very nice thing to work with as well. But in fact, Heckenberger and Kolb didn't really do it for CP2. They did it for a very large class of spaces, and these are the ones that I was looking at since my PhD. So you start up in the very middle, you've got quantum CPN, of which the motivating example is quantum CP1, the Podlesh sphere. Then more generally, from projective space, you can go up to Grassmannians. The definition of them is there, it works. The calculus exists, the cuneiform de Rham complex exists, the complex structure, everything carries over and works very, very nicely. This is, I was talking earlier on about the series, these A, B, C, D. The Grassmannians are the A series case of the Drinfeld-Jimbo quantum groups. You can, in fact, go outside of this to the B, C, D, and the subclass of flag manifolds that they looked at there are known as the irreducible quantum flag manifolds or the quantum Hermitian symmetric spaces, and everything works for those as well. They admit an essentially unique UQ of G covariant Q deformation of the classical Dolbeault double complex. Okay, so I'm now, because these things have started to become reasonably well understood, there are still many questions we do not understand, but we understand enough that it's time to start seeing if we can extend beyond this. And let's look not at this quantum CPN and so on. We're looking at something somehow at the opposite end of the spectrum, where these irreducible flag manifolds, they can be realized classically as quotient of your semi-simple group by what's called a parabolic subgroup. And the irreducible ones are the ones for which the parabolic subgroup is the largest. So what we're going to do is look at the other end of the spectrum and look at the one for which the parabolic subgroup is the smallest. And that basically is quotienting out by the maximal torus. And the intersection of these two things is Podlesh, because there the maximal torus and the parabolic subgroup actually coincide. So one thing about looking at quotient by a torus is that the representation theory is simpler, of course, for a torus than it would be for a general parabolic subgroup. And that basically implies, I'll ask you to believe me, that all of your homogeneous vector bundles, equivariant vector bundles, equivariant finitely generated projective modules are going to be sums of line bundles. This is a general fact when you look at the full flag manifolds, full being the quotient by a torus, that's the name for it. So for any G, we have a Q-deform subalgebra, just analogous to what happened in Podlesh. It's going to be Laurent polynomials again, but in a number of generators depending upon the rank. So for SL2, the rank is 1, so you've got 1 generator, and it's inverse. Then that will give you this decomposition, just in the same way that we had a decomposition of SU2, OQSU2 into these line modules, these invertible, these quantum sections of line bundles. This carries over directly, where this is the weight lattice. They're just copies of Z, and L is going to be the rank of this in the weight lattice. And we call the subalgebra here E sub 0. Remember, for Podlesh, we had our Z copies of, we had Z line bundles, a line bundle for every integer. Here we're going to have tuples because the rank has gone up, and the rank of the Lie algebra, that's the number of copies of Z that you have. And they label the line bundles, quantum line bundles, the line modules over these things. And as before, the degree 0 part, that's which is what is by definition the quantum flag manifold. So a direct generalization of Podlesh to all of these Jimbo guys. Okay. From now on, we'll restrict to the A series, which means that we will denote the full flag manifolds by OQ of F n sub 1, the n sub 1 matching the n sub 1 on SLN. And the question is now, what happened for Podlesh? What happened, in fact, I guess, for the irreducible quantum flag manifolds? Do we have some sort of a Q-deform Durand complex for these things? But to do that, so the way that Heckenberger and Co. constructed their deformations, they used a uniqueness result. And they were able to classify them in this, this essentially unique project or conditions that I described or roughly referred to. This will not work once you go outside of the irreducible. So you need to do something else. You need something more solid to hold on to. And the way we do this is Lustig's root vectors. So we want to basically construct our calculus in a sort of a formal way. And the way to do this, the way to associate the construction of the calculus to the structure of the quantized enveloping algebra itself, is to look for a tangent space, a so-called tangent space, a quantum tangent space. In the classical setting, the tangent space of your full flag manifold is just going to be the positive and the negative part of your Lie algebra. If you think of the triangular decomposition of G into the positive nilpotent, the negative nilpotent, and the cartan, if you just remove the cartan, because we've been quotienting out by the maximal torus, what's left classically is the tangent space for the full flag manifold. So we'd like to see, could we mimic that and have somehow a more streamlined, a more conceptual construction of the calculus from a Lie theoretic point of view? So what you would do then, we would look for the replacement, the quantum Lie algebra G that lives inside in the universal enveloping algebra G. Remember that classically it's a Lie algebra, it's non-associative. This is difficult to work with. So you have this object called the universal enveloping algebra, which turns it into something much larger, something infinite dimensional, but it's something that's associative and hence easier to deal with. What they found when they were quantizing these things is they found the Q deformation of the universal enveloping algebra, not of the Lie algebra. And it's something that's still not understood all these years later, what the quantum Lie algebra inside there should be. However, what we do have is an analog, a quantum analog of the,
right?
No,
That's correct. So, I mean, is there any hope of having something like that, or would you have to do something?
Yes, it won't be a Lie algebra. That's the thing. Basically, what's going to happen is that the Lie bracket that you have would be Q deformed. So it's how to Q deform the Lie bracket in a coherent way, and what axioms it should then survive, so it should then satisfy, and so on. And so this is the question. So, you know, we understand part of it, but not the whole picture.
It's easy to see what should be a bracket, but
yeah,
it should be a property. It's mystery for 30 years.
However, we do have very natural deformations, Q deformations of the positive and the negative part due to Lustig. So if we look at the A series, how does this constructed? How is this defined? You take the braid group on n strands. That's just a cover of the usual symmetric group in the A series. So what is it? Just says that if our two generators are far enough apart, which is to say the difference between their indices is greater than or equal to 2, then they commute. If not, then you have what's called the braid relation. So you can you have I plus 1, I, and that's going to be equal to I plus 1, I plus 1. So you can sort of do this braid move where you change the braiding somehow. And that's what happens when these things are next to each other. And that's what makes this interesting, but what makes it challenging and complicated. Then we see that we have a surjective map from the braid group onto the usual symmetric group from here to here. What happens is basically adding in the relations that SI squared is equal to the identity. Okay, because that's in the symmetric group if I have two things and I swapped them. This is the permutation, just two elements swapped. If I swap them and then I apply the same thing again, they go back, so it's the identity. In the braid group, you've removed that relation. But of course, you do have a surjective map. And somehow, in some sense, this transition, this generalization or this lift from the symmetric group up to the braid group is analogous somehow, at least related to the transition from the classical to the quantum. You could say, you know, when you have an electron and you rotate it once, it doesn't actually go back to where it started. You have to do it twice, something weird like that. And now a breakthrough result of Lustig was to use the braid group, this kind of replacement for this symmetric group in the quantum group setting, at least in the A series, was to show that there was an action of the braid group on the universal enveloping algebra, okay? And it's an algebra action. I won't define it because the definition is quite technical, but it is there. And it sends every generator of, sorry, that should be a sigma because we're in the braid group, not an S. It sends every element of the braid group to one of these linear operators on an algebra operator, sorry, an EQ of G that we denote by T sub I. So then with this, you take the Weyl group of G. So here, actually, I said we were going to look at the A series from now on, but I have actually just kept this in the general setting. So you see that it does extend across. You take the Weyl group, in our case, the A series, just the symmetric group, and you look at the longest element of the Weyl group. It's a finite group, so it has the longest element. This is a well-defined notion. But then there are a number of ways to express the longest element of the Weyl group. There will be ones which are shortest. That is also well-defined. And then you have a collection of these reduced decompositions, reduced presentations of the longest element of the Weyl group. And what Lustig realized was that the choice of negative and positive root vectors is actually sensitive to this choice of decomposition. In the commutative case, for classical Lie algebras, it reduces down to the same thing. But in the quantum case, you actually need to make a choice. And when you do that, you can mimic. So in the classical case, if we were to take this action here, this would actually produce our positive root vectors and negative root vectors, and hence give the positive and the negative part nil radical of the Lie algebra. Here, it just becomes a definition, okay, and he calls them quantum root vectors. Now, anyone can make a definition. Why is this thing actually of any interest? It's of interest because if you take this basis here, which in the classical case is called a PBW basis, it's the Poincaré-Birkhoff-Witt. This gives you a linear basis of the universal enveloping algebra, which has amazing properties and is a central result when people are working with universal enveloping algebras. When you're talking to somebody about universal enveloping algebras of Lie algebras, semi-simple Lie algebras, and you're trying to ask somebody how you would prove something, a lot of the time what they will do is go back, well, okay, well, let's start with the PBW basis and we can go from there. So what Lustig wanted was an analog or a generalization of this PBW basis for the quantum setting so that you could, you have a similar tool in the quantum setting. And it turns out that his intuition about using the braid group to define the root vectors was correct because you have the PBW basis. And this went on to have huge implications.
Stupid question, and maybe you already said this and my brain was somewhere else, but what does this have to do with the actual braid group rather than just the Weyl group?
Because it's a group homomorphism from the braid group into the endomorphisms. It would not satisfy S squared.
But I mean, this you're just writing down as longest elements of Weyl group.
Yeah, it goes back to, it's here. No.
I mean, I don't see where the definition is coming from this action.
Because T. This is your reduced decomposition, and then this gives you.
Okay.
You
Thank
take
you.
reduced, yeah, sorry. This was the starting point for very, very deep consequences came from this. In particular, let's say the theory of canonical bases, which is one of the major applications of quantum groups to classical representation theory, went on to have many fashionable consequences, things like categorification. You know, this is one of the starting points for this. So it really is a very, very important thing. And that's why we were like, okay, if we want to extend beyond the second order Kolbe setting to look at tangent spaces for non-irreducible flags, we don't have this uniqueness classification. So we want something more solid we want some solid starting point. And we said, okay, why not start with this amazing invention, discovery of Lustig, and then actually sort of change our point of view a little bit. We're really maybe no longer trying to look at non-commutative geometry for the flag manifolds, but instead maybe what we're actually doing is using non-commutative geometric ideas to examine this thing here. Okay, we're kind of turning things around. And maybe what's the point of all of this non-commutative geometry? We'll go, okay, well, maybe the point is that we can actually use the geometric ideas to examine something which is definitely a very, very important structure. That's kind of where we're going.
Great, I have another question.
Yeah.
I mean, it makes sense to talk about the longest element of the Weyl group for a Weyl group, but I guess in the break group, there's no longest element.
It's infinite dimensional.
Exactly.
Not
So-
infinite
So
dimensional.
what happens, for
Infinite
example,
group.
if you take a longer element in the break group and act on
do
these things?
something like this.
Like what it's, how, I guess I don't see why the longest element comes into play.
In the break. Yeah, back up. But I mean, that's. Yeah, you're identifying a special element in the break group, yeah, by splitting it back up. I guess because classically, the longest element of the Weyl group is the thing that, you know, via this, what is classically a result, it's a result that this operation will actually give you all of your positive and negative root vectors.
Okay, another term,
And this is expressed in terms of the longest element of the Weyl group.
and these are honestly different elements of the break group.
Once you lift it back up, yeah.
So.
Well, no,
You're just
no,
trying-
no, this is not true. No, this is not true. No, they're not different because
You different elements.
this is the nature of the action. I mean, it's a fact.
But I mean, okay, that's not really a group action then, is it?
Yeah.
But if these TI1, I2, like if there's a different choice and they give you the same element of the break group, how is this giving you a different element?
All right, you're saying that this is a, right, I'm saying that this is a group homomorphism. We have the representation of this. Am I saying something stupid that this is a? I have to think, maybe I've said something. I don't think, they are, yeah, sure, I understand. They are genuinely different. I mean, you'll see it in a concrete example and stuff. So anyway, that was abstract general things. Let's go down to some concrete examples and actually see what this looks like. For SL2, the Weyl group is S2, so the longest element is S1 and the corresponding positive root vector is E, and the negative one is F, so this is easy. For the case of SL3, the Weyl group is S3, the longest element has two reduced decompositions, S1, S2, S1, S2, S1, S2. These two things are equal, it's just a braid move between the two of them. And now what are the different, if you go through the process for that Lustig described for defining your root vectors, one of them gives you E2, E1 with a Q, and the other one gives you E2, E1 with a Q inverse. And these two elements are not proportional to each other. So it is a genuinely different thing. If we go up a little bit higher, we see that the Weyl group of L4 is S4, the longest element is 8 commutator classes of reduced decompositions. You can see here they are. So now, just for the sake of space, I'm after dropping the S's or the sigmas, and I've just written the sequence of numbers themselves, the indices. Hopefully that makes sense. And you can see that to go from here to here, it's a braid move. And another thing that I haven't mentioned is that, in fact, it's not actually all of the reduced decompositions, because if the reduced decompositions differ by a commutation of two elements that are sufficiently far apart, then they give you the same root vectors. It's only when your root vectors, so only when your longest element decomposition differs by a braid move that you actually get two different root vectors. That's the thing. So here, there are actually other reduced decompositions inside in this class. So for example, here, the 3 and the 1 I can flip, and it will be the... Yeah, absolutely. Yeah. What's missing in the braid group is that the square is the identity. Yeah. You can flip those in the braid group as well, and that will give you the same root vectors. And that's, you know, after looking at it for long enough, it's actually easy to see this. But it's, then you see what we've done here is we got 1, 2, 1, and we flipped this, so they have braid move to 2, 1, 2. And these are your commutator classes, they call them. It's two things are in the same commutator class if they differ by commuting two elements that are far apart. Counting the number of commutator classes for any Weyl group is actually an open combinatorial problem, even in the A-series case. It's equivalent to many other things in combinatorics, that's always happened. There's some upper bound proved by guys in Malestrana, actually, very different point of view. But what do the corresponding root vectors look like? Well, here you are. So the simple root vectors, the E1, E2, E3, the simple generators, I haven't included these here for the sake of space, and they're always the same. But what you'll see is that the different choices have basically put, and I've also, for the sake of space, to fit everything on the slide, I've replaced Q inverse and Q plus by a plus and a minus. And you'll see that you get, at one end, this decomposition and the other one, these are the ones at the extreme ends. Here, these are the nice ones, they behave much better than the ones in the middle. The closer you get to the middle, the more complicated things become. And you can see that here because up in the top, everything is, you know, you're counting down and it's all minuses. Here, you're counting up and it's all minuses. You go into the middle and things get messed up. And in fact, what Petra and I found just by messing around is that the one at the top and the one at the bottom are really the ones that you should look at from the point of view of noncommutative geometry. Uli, in fact, when he was here a few weeks ago, explained to me that he wrote a paper 20 years ago that explained why these guys were actually the important, were the relevant ones to look at from a different point of view. Yeah, but these are counting, one of them is counting, this is counting up, 2, 3, this is counting down. This is kind of the other one is counting down, so you mix it up.
1, 2, and 3, 2.
1, right.
And then 1, 2, 7, 8, 3 plus.
I know I'm lying, sorry. Actually, to put space, what's going on here? Okay, sorry, I'm confusing myself. So there's a symmetry around the middle. If you put a line here, this one and this one is basically the same thing. You've just changed the ordering, okay? You can count 1, 2, 3, or you can count 3, 2, 1, and basically the group is the same. It's just reversing the labels. So anything that happens on this side is just a reflection of anything that happens on this side. So what I've done is I've just included these 1, 2, 3, 4, and 5. Okay, sorry, I've given this part of the talk too many times, so I'm trying to go through it quickly because so many people have seen it before. But unfortunately, in the process, I'm making a mistake. So what you see is that, in fact, we should have the same number of these again down here, but it will just be a reflection. You'll just change the numbering that you have. So in fact, the worst behaved are these two at the end. They're the ones where everything is more chaotic. And they're the ones you don't want to use. You want to use this one and the corresponding one here that I couldn't fit. Okay. So what we did, what I did with Petra over the last number of years was to then define our tangent spaces, these quantum tangent spaces. I'll explain, I realized that I started off with differential calculi, non-commutative Durand complexes, and now we've gone into representation theory. We'll go back in a second. We're going to construct our differential calculi from these things here. So you just define, you've got your positive and negative root vectors. You define those to be you call it T10 and T01. So that is to suggest that they're the tangent spaces of the holomorphic and anti-holomorphic part of our calculus that we hope to construct, where these are Lustigs, positive and negative root vectors. And we now restrict to this reduced decomposition because that's the one that behaves best. We could have restricted to the one that counts up. You see what's happening. We've got 1 n minus 1 and go all the way down to 1. Then in the next step, we forget the 1 and you go down to here. And then in the next step, you forget the 2 and so on. And eventually you get down to 2, 1 and 1. You could just equally, you could count up 1, 2, 3 up to the n, and then you would go 1, 2, 3 up to the n minus 1 and so on. But no, yes, it should, what, it's n, and then you've got the, yeah, that's a typo. Wow. Thank you. It should go down to n minus 1. Okay, you can see what's happening. So then calculation with Peter for the positive parts, and then with Ale and Junaid for the negative part. Although as Uli told us, if you look at this from an L functional, a coquasi-triangular point of view, this is actually easy to see, which is something that was very, very good to learn. Moreover, if you act on it by the quantum cartan, it would be a submodule with respect to the quantum cartan. Why do we care about these properties? Because these properties are precisely what a subalgebra in the universal enveloping algebra should satisfy so that you can build a calculus from it. Okay. This part is basically comes from the construction. It's easy. It just means that these things are root vectors or eigenvectors of the k's inside the new cartan. That's the one that was a bit more. There's a calculation to prove it, although as Uli has now shown us, it's actually reasonably clear as well, which is very good, because that means it extends to the other series. But anyway, how do we construct a calculus from this tangent space? You kind of follow the classical situation. So we're going to take OQ n as the algebra that we're looking at. That should be n plus 1, sorry. OQ n plus 1. And then we're taking this box, whatever that means, and then we're putting t. So, or we can duly look at it as O of t, if that makes more sense to you. So what we're doing is this box here indicates that we're looking at a subspace of the tensor product. So this thing lives inside of the tensor product, and it's somehow a balanced subspace of the tensor product that in the classical case would give you the homogeneous vector bundle. And classically, if you're over a homogeneous space and you have a representation of the subgroup that you're quotienting by, that will give you a vector bundle that somehow carries a coaction, carries an action, an equivariant vector bundle. And there's a bijection between these things, an equivalence of categories even between the representations of the subgroup that you're quotienting by and these homogeneous vector bundles. And that is basically the Hopf-algebraic non-commutative direct generalization of this. So these are the sections classically of the vector fields over the space. And then we dualize up to this. We can formally dualize this because it's a module over the cartan part. And then that will give us the one forms. Okay, it's again a tensor product over the dual module. And what magically crops out of this, the conditions that were given on the previous slide, tell us there now exists an exterior derivative, linear map satisfying the Leibniz rule that goes from your functions up to here. And that's how you construct calculi very quickly from tangent spaces. But moreover, we can then extend this up to, in a very formal way, we can extend this up to a Q deformation of the Durand complex, the whole Durand complex. And that is actually quite easy. Once you've got the degree 1 part, the rest will follow. Calculating the dimension of this thing is more problematic and confirming that it's classical, but it does exist. Before we do that, as I said, any one of these homogeneous vector bundles over the space will be a direct sum of line bundles. Actually, the line bundles in this case are going to be indexed by elements of the root lattice. This is this sublattice inside in the weight lattice. Exactly as it would be classically, and just like you have for Podlish, something that doesn't happen for CPN or for the irreducible flags. If you can now ask what happens if we go down to the case of Podlish, the one that we saw before, then in that case, the root lattice is spanned by, the root lattice is, the space of roots, this is not the root lattice, this is the space of roots, is given by twice the fundamental and minus twice the fundamental. And hence that means we get back these two line bundles, the -2 and 2, that were already known for Podlish as shown by Sharon. So it's a direct higher order generalization of the situation with Podlish. No, as I was saying, we can formally extend. I won't give you too much of the details here, but it's sort of it is a generalization to the non-commutative setting of the exterior algebra, one that is universal in the sense that any other extension to a differential graded algebra will arise as a quotient to this universal one. It's the largest extension possible. So we can formally extend to this, and with some heavy calculations, or a PhD student. So this is Junaid Razak, who is in Bologna, who is the PhD student of Rita, who was visiting us here for a couple of months last autumn. Did some heavy calculation here very well, very quickly and efficiently, together with myself and Ale. And we showed that the maximal prolongation of this first order, this calculus that's coming from Lustig's root vectors associated to this nice reduced decomposition of the longest element of the Weyl group, it has classical dimension. Everything works exactly as you would want, generalizing up to the next setting, the Podlish situation. You notice it's 6-dimensional because the full flag is 6-dimensional. SU3 is going to be 9-dimensional. Am I right? No, it's 1, 2, 3. We've got 3, 3 is 9, minus 1 is 8, and then 8, you take out the torus, which is 2, and you're left with 6. So now the question is, this is the de Rham complex, the direct Q-deformed. Lustig basically knew all along with these tangent vectors that there was, it gives us this canonical non-commutative geometry associated to this thing. The question is now, does it break up into a diamond, a non-commutative Hodge diamond? Well, before we do that, you see that the line, all of these omega k's, they also decompose into line bundles that you can figure out reasonably easily, because they're just the same as they would be in the classical case from the exterior algebra. And what about the non-commutative geometry, though, the non-commutative complex geometry of these calculi? To do that, let's actually introduce a definition that formalizes the properties that we have seen for Podlish and for CP2, and more generally, we hinted at for the irreducible flags. This is something introduced by Edwin, who's with us, and Paul Smith, but also at the same time by Kalkali, Landi, and Bosoilicum, an almost complex structure for a total differential star calculus. You could just take this as a non-commutative de Rham complex, is a refinement of the usual N2 grading of this differential graded algebra into an N2 grading. And you see here, so you want the K forms are going to break up into a direct sum of AB forms such that A plus B is equal to K. And that, if you think about it for a second, actually gives you the diamond. Although in the non-commutative setting, it's not clear that the exterior algebra will actually finish at the corners. In all of the examples we have, it does, but it's not guaranteed to happen. So it's not guaranteed that you get a diamond, that it actually terminates and comes back, but at least you would get some sort of a shape like this, okay, sort of a cone. Moreover, we want this thing to have a star. We want this to have a star map. So a conjugate linear map that is a graded anti-algebra map. And it should flip the AB forms, because that's what happens classically when you take the complex conjugate, you go from AB forms to BA forms. Moreover, if the exterior derivative decomposes into the direct sum of two maps, del and del bar, where the degree of del is 1, 0, and the degree of del bar is 0, 1. It's uniquely defined if it does exist. So it should just be that when you take D of a form, you will have a piece that lands immediately up to the right, immediately up to the left, and nowhere else. Then this thing is called integral. In other words, we will get a double complex from this. Why is this interesting? Why do we split it up into two parts? Because classically, for any complex manifold, you have one of these. Sorry, for an almost complex manifold is a manifold with one of these on its exterior, on its de Rham complex. Any complex manifold will have one of these, but having one of these does not guarantee that your manifold was complex, that the transition functions on your manifold were holomorphic. But a deep result, the Nylander-Nierenberg theorem, I think he's down there at the back of the hall on one of the posters. Big. Oh, maybe it's outside. Is he? Yeah, okay. Turn the camera around. So they proved a very deep result that says that one of these on your manifold comes from a complex structure if and only if it satisfies this. So this condition about the holomorphicity of your transition functions on your manifold downstairs can be turned into a completely algebraic condition. And that means then in the non-commutative setting, we take it as a definition. Okay, so that's just some formal setup to understand what we're saying. Looking now at the classical case at our manifold, the full flag manifold of SU3, it has more than one almost complex structure. If you look at equivariant complex structure, so one that interacts with the UQ of SLN plus one module structure, as everything should be, because that's really the thing that we're trying to examine. We're using the geometry to understand the structure of UQG. Then classically, you've got 4 almost complex structures. When you're in the irreducible case, there's only one, up to opposite complex structures, which is just basically a choice of convention. But once you go outside to the full flag manifolds, you've got a lot more freedom and a lot more for more interesting phenomena to happen. So classically, you want to break up your one forms into positive and negative. And then if you do this, that completely determines the decomposition for the rest. In the commutative setting, this is always guaranteed to exist. In the non-commutative setting, it is not guaranteed to exist. But once you determine it at degree 1 and check, that tells you everything. So we will take the decomposition, not of the one forms, but equivalently of the tangent space. And you see that you have this 0, 1, you pick a subspace, you need to pick it on basis elements because these are root vectors, these are weight vectors. So if it's going to be equivariant, there's no order choice. So it's a question of basically assigning to each of your basis elements, put it into the camp of 1, 0, put it into the camp of 0, 1. Then you see that that's going to give you a choice. You're basically going to get 8 almost complex structures. Okay. But as I said, whether you call something 0, 1 and the other 1, 0, or you call 1, 0, 1 and 1, 0, it's basically two labels for the same thing. So you cut out half of them, and what you're left with, you're left with 4 almost complex structures, classically. And this works in general for all the full flag manifolds. It's going to be 2 to the rank -1, if I remember, or 2 to the number of almost complex structures is 2 to the number of positive roots -1 when we've identified opposite complex structures. Okay, so what are they? The simplest one, the most natural one is that you call your positive root vectors the 0, 1, and then of course, correspondingly, the F's are going to be your negative root vectors. Another idea is you can put an F in here and take this E1 and put it into the other camp, and that will give you an almost complex structure. Or you can put the middle one into the other camp, swap the middle two, or you can swap the last one. Okay. And then what are they? Well, for the integrability condition, the first 3 classically are integrable. The last one is not. Okay, so this is one of the simplest examples of a non-integrable almost complex structure on a homogeneous space. The first one, which is the most natural one, is actually a Kähler manifold. What is that? It's like Riemannian for a complex manifold, plus a lot extra. It's a simple condition, but with deep consequences. Here, it's just basically, it's like a Riemannian metric on a complex manifold that interacts with the complex structure in a nice way, but not as nice or not as strong as Kähler. This one is also Hermitian. And the last one, it's not complex, it's just almost complex. And the corresponding metric that you have there is what's called nearly Kähler. I won't go into this, but very interesting structures as well. So now, question is, when we start to look at the almost complex structures and the metrics actually on these spaces in the quantum setting, what do we get? What does this table actually look like? What turned out to be very surprisingly, so what we really wanted to do, what I wanted to do in particular, was to construct a non-integrable, almost complex structure in the quantum setting. And this seemed to be the place to look. And I thought about this in my head before, a number of years before, and everything worked, and I had it proved. But when Junaid came, I knew I had somebody who could calculate, and we could actually write this thing down for sure. And it turned out that actually what I did in my head was wrong, unsurprisingly. And it turns out that this thing does not actually exist. It's not that it's not integrable or anything. This decomposition does not make sense in the non-commutative setting. Why? Because it turns out that the decomposition, the associated decomposition of your 1 forms into 1, 0 forms and 0, 1 forms should be a decomposition of bimodules. Of course, it would be ridiculous to have it just left modules or just right modules. It should be bimodules. And for these 2 cases here, the associated decomposition of your 1 forms is only a decomposition as left modules and not as right. So this almost complex structure in the non-commutative setting does not exist. This is something that really happens when you go outside of the irreducible setting, because the action on the joule of the tangent space is not via the co-unit, it's not trivial. And that gives you a non-trivial action on the right, which basically eliminates these possibilities. However, these 2 do exist, and they are integral. So my hope of constructing a non-commutative, non-integrable almost complex structure, well, it didn't work out. I'll have to wait for another day. Yeah.
holomorphic or anti-holomorphic.
No.
Yes.
It's not a bimodule. It's as simple as that. Yeah.
All right.
It's just basically if you take the associated omega 1 0 and you multiply it, you land inside an omega 1 0. You can possibly land inside 0.
So I guess one other way, one equivalent way.
Sorry,
to
Ali,
say this-
just 1 second. Andreas is finishing.
Sorry.
But could you mix them together? For example, you take two
I don't see.
holomorphic and anti-holomorphic, they left, and try to introduce artificial.
That is somehow what's happening in this one. You're mixing it. That's the only way you can kind of mix it up. It doesn't work. So you see in particular that the non-integrable ones, the non-integrable one has disappeared. We have no non-commutative non-integrability. Sorry, Ali.
Yeah, I was just making a comment that maybe another way to see this is that T01 for the second choice, for example, is not a tangent space. It doesn't respect the coproduct condition.
Yeah. That's another way to, exactly. These decompositions are not tangent spaces. Yeah. Thank you. Anyway, so this is what we've done and what we saw for the case of SL3. Then the natural thing is, what if we go up and see what happens? So the calculations become more complicated, and that's why we haven't really gone there yet. But there's a number of things that we can conclude without actually having to do the calculations, just using some representation theory and a couple of tricks. Turns out that, okay, as I said earlier on, in the classical case, the number of G invariant almost complex structures is G2 to the power of the number of positive roots. This Newlander-Nierenberg theorem tells us that an almost complex structure is integrable. So this is an equivalent formulation. Before I said it was that the exterior derivative is equal to the sum of the del and del bar. That's equivalent to this condition here, that the commutator, the integrability of your subbundle, as classical geometers would say, that the commutator of these two things, it's closed under commutators. That condition here actually turns out to be the same thing as asking for a subset of roots, a base of your root system. It's asking for a subset of roots such that for any two roots inside in your subset, such that their sum is still inside in the root system, then we necessarily have that this sum is inside an OR. Okay, if you think about that for a second, if you know a little bit about root systems and Lie theory, you'll see that this thing here, this integrability of one of these almost complex structures here is the same thing as choosing a base for your choice of root system. If you don't know anything about root systems, then in this classification of Lie algebras that you have, you basically turn your complex semi-simple Lie algebra into, or you associate to it a root system, and then you classify these root systems, and that's what gives you the classification, because you've turned, I guess, well, first of all, you take your Lie group, then you turn it into a Lie algebra, and then you turn that into a root system, and then you're in combinatorics, and you can use the combinatorics to classify the original Lie groups in this very beautiful result. Turns out that then this root system, the tool in the classification, or even the study of the algebras, there's an notion, an analog of a basis for a vector space, basically. And that's what a base is in a root system. And turns out that they're equivalent to the integrable almost complex structures on these flag manifolds. Yep.
But for example, vector spaces in universal enveloping algorithms, you have a quantized right of the left vector is the joint action as it goes.
Say that again, sorry.
So you have a quantized joint action of your
Yep.
You have your vector.
Yeah.
So it's acts on itself.
Yeah.
Well, it's closed or
It's quite closed under.
this is position.
You mean is the T10, these ones? Yeah, because the the Lustig root vectors in the nice case at least are built up by continuous actions, but if you keep on going, I think you will get extra pieces. I'm not sure. It's reasonably easy to check though, but I'm not sure it's that easy. So in the general case, we have, and this is kind of what I was saying earlier on in the SL3 case, we have a decomposition of the full flag manifold into a 1, 0 and a 0, 1 part as left modules, okay? And they do in fact respect the coaction of OQSUN plus 1, or equivalently the action of UQ SLN plus 1. But they're not as right modules, because the right action is non-trivial, because now we're outside of the irreducible setting, the Heckler-Markov setting. Things become more complicated or more interesting. And it turns out that we do not have, the number of decompositions we have are not given by the number of positive roots, the upper triangular, strictly upper triangular matrices or strictly upper triangular entries. They're given by the what would I say? They all fail except for a subset that are indexed by the simple roots. So we're going, that's when we pass to the non-commutative setting, we go from having positive root vector number of almost complex structures to simple root vector almost complex structures. So quite a nice result. What result we were pleased with, at least. What does this mean in some kind of conceptual or philosophical way? We don't know. And all of these, well, this should be on the next slide. In fact, this differential calculus, so they're doing the process for full flag manifold of all orders, has no integral almost complex structures, and it has at most 2 to the L complex structures. We conjecture that it has exactly 2 to the L, but that's where we need to do the calculations to actually see what the relations look like in degree 2. So for these spaces, at least, non-integrability is a classical phenomenon that disappears when you go to the quantum setting. Now I have 1 minute left, so this should hopefully. No, the question is, I was speaking a bit about these things, about Kähler metrics. So you would like to put a metric, a Kähler metric, a Riemannian metric on these, or a non-commutative Riemannian metric on these calculi, so that you will then be able to get an inner product, and you'll be able to take a completion. You have a Hilbert space and so on. You can look at things, these non-commutative differential operators, or one can also look at the adjoints of the operators, which give you these Dirac operators, which have associated Hodge decomposition, which have cohomology theories, which, a lot of very interesting and very beautiful stuff. There is no time to discuss this, so we leave it for another day. But things actually, at least for the case of the full flag manifold of SL3, it does work as one would expect. And there were not as many surprises as there are with the almost complex structures. And we expected this will work for the higher orders as well. I think that's a good place to stop. And thank you.
Do we have questions in the audience? Okay, it's look like not the case. Do we have questions online? So please unmute yourself and.
Ciao Ramon, this is
Ciao,
Rita. Can you hear me?
Yeah, I can hear you. Yeah.
Yes, so I'm interested for different reasons to look at the tangent space. And I was looking at it with Alessandro yesterday, and we had a different definition due to Voronovich that was a bit more, restrictive somehow. So did you look at that?
This is coming from the bicovariant calculus.
Yes, yes.
Yeah.
So how is it related with yours?
Well, it should give you, it's just that these things are not bicovariant calculi because they're homogeneous spaces. So you've quotiented out on one side. So even classically, you only have an action, a group action on the left. So bicovariance doesn't make sense. So when you're in a homogeneous space, you can't use Voronovich's condition. But Voronovich's tangent space should give you a tangent space in this sense, though.
Okay, thank you.
So somehow the notion of a tangent space here is more general. And then Voronovich's one would be an example. But the Voronovich construction can't work here, even in the classical case, because bicovariance doesn't make sense.
All right, do we have more questions? Okay, thank you. Oh, okay.
Okay, so this is a calculus for the full flags, and you already have done this for also irreducible flags. What about guys that are in between? Does this offer any insight there?
Yes, I didn't really have time to mention this, so thank you very much for the question. It works. So the ones that are in between, they're going to be subalgebras. When you've got a subalgebra, and if you have an algebra B contained in an algebra A, and you have a calculus in A, you can just restrict to a calculus on B. This is easy. And if you take these calculi, the partial flags live as subalgebras of the full flags, so you can restrict down and everything works. At least on the anti-holomorphic side, because we haven't really, but if you do it here, if you take for this example that we looked at, for the whole Dolbeault complex, you have 2 copies of CP2 living inside in the full flag. And then if you restrict this calculus onto that, you're going to get the Heckenberger code. It restricts down to this, which is a test that we wanted to run by to make sure that what we were doing was actually sensible. It should generalize with Heckenberger and Kolbe-Dunne. Yeah. And that will work for, at least in the anti-holomorphic part, this will work for all the A-series partial flag manifolds.
And these will also be almost complex, integrable, blah, 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 blah.
This we don't know actually, because we haven't looked at it yet. Because we're just looking at the anti-holomorphic part. So then you don't have the DRAM. Well, you don't have something on which you can put an almost complex structure. So well, these days I would have said that everything would have carried over, but with the surprises that we have here, that the non-integrable ones and more disappear, I'm no longer sure what actually happens. So that's an interesting question and something we will look at in the future.
Braided tensor product, but it's a usual tensor product of algebras because of braiding.
Mhm.
It's very simple. But
Here, who knows? Yeah, maybe. I mean, these things, at least, they are factorizable in the sense that omega of AB is, the AB breaks up in tensor product of A0, B0, or B0, A0, which means that you do have some sort of a generalized braiding between these things, but what it looks like, I don't know. Well, I do to some extent.
But
the full complex is just a tensor product.
Yeah,
No
I
braiding.
mean, at least as vector spaces, it's a tensor product.
No, as an algebras.
Hmm?
As an algebras, no?
Uh,
What is a cross
I
relation?
mean, it's the same as for Heckenberger code.
But then you use a braiding for Levy. Your Levy now is Storos.
I mean, you have to, yeah, as you said, if I multiply in an AB form, but in an A prime, B prime form,
Mhm.
I have to commute things through. I mean, there were commutation relations there, and then that lands you inside an A plus A prime, B plus B
Yeah, yeah.
prime. But what form these commutation relations take in a more conceptual way, I don't know. I mean, in the same way, yeah, for Heckenberger Kolbe, it's even still a bit mysterious. Well, yeah, but that is braiding with respect. Anyway, we can talk about it later. Yeah.
Ask more question, Ray, or let him go? Okay, thank you for a very nice talk and very nice discussion. So will we announce the next talk? It should. Ray, could you open the?
I don't know. Can I?
All right. So the next talk will be by Manish Kumar from IMPAN, and it will be about factorizability and finiteness of Q-Arakari woods of one-Neyman algebras. It will be online again and in person in GitNam. So, Sarah, thank you very much for attending our seminar again. See you next week. Bye.